The experiment is going to show the relationship between electricity and magnetism. And look how simple this experiment is. Electric meter here that we can use to take some measurements. Have a battery. Here's a magnet. Have a coil of wire and a compass, which should be pointing north. And so the Earth has a magnetic field, which is causing this compass that's magnetized to point a certain direction. Okay. Watch the compass over here. Well, what we're going to do here is we're going to take this electric meter, and what it does, it's going to measure the current, or amps, very small amount of amps flowing through this wire. Okay, so I take my two wires here from my meter, and there's a point here at which one end of the coil is here at the bottom, the other end of the coil here at the top. And let's see, my meter, now the videographer should come close here to look at the meter, because we want you to make sure that you see that you're going to be looking at the needle. All right. Now, can you see this part of the meter at the same time that you see this coil? Can
okay,
you?
yeah.
Okay.
Nobody else can see it, but I can see
but,
it.
But if you want, you can come up if you want to see this, because it does illustrate something. All right. Now, I'm going to try not to touch the table, because otherwise people will accuse me of well, if I do this, see the meter kind of jiggles there. Mm-hmm. But we're going to try not to hit the table. I have an earthquake right now. So I'm going to take this magnet, and I'm going to push it down through the hole and pull it back up. And I want you to watch the needle very carefully. Is there movement? Well, yeah. You're probably going to say, well, the magnet is doing something to the needle. Let me get this away from there. All right? I don't want any influence. Go way over here, and then go back and forth.
It's moving. So that measures electricity?
That's correct. And what's happening is the magnet going through the coil of wire here is actually doing would you want to try to explain? There's a force going on here, and it's pushing electrons and what have you. Mm-hmm. How would you want to?
Well, what James Clerk Maxwell discovered in the 1800s was that a changing magnetic field produces a changing electric field, and vice versa. So that's exactly what's going on right here. We have a magnet that's changing and causing an electric field around this wire, and that translates into a little jump in the needle over here. So there's a lot of complex math involved.
Okay. The other thing is, this concept here is no different than what the giant power plants with generators have. It's the same concept. It's a magnetic field crossing through some coils, and then as such, and then the coils are producing or forcing the electrons to be pushed out, and we generate electricity that way. It's just what costs so much to generate electricity. It's not necessarily the coils or the magnet per se. It's the energy it takes to move the magnet through the coil. So and a lot of that has to be done usually with a steam turbine, whatever, that's spinning, and which will actually rotate magnetic field around the electric coils and produce the electricity. So you can still see the little needle move. In reality, for power that you get out the wall, that little needle will be going back and forth 60 times every second. That's what that would represent.
Back and forth. What do you mean?
Because what I'm doing, if you notice, I push one way, the needle deflects one direction, and when I pull it back out, it deflects back the other way. So that's like this is measuring DC current, which means it measures the direction it goes direct. But when I force the magnet back and forth, it's alternating. So that's like AC current, alternating current, because it's back and forth. So there it goes, back and forth. I don't want to touch the table. So, well, we can make the magnet produce the electric field. Well, guess what we can do next? We can take Here's our handy compass here, which is, we don't even need the, let's see how we're going to do this. Yeah, we will use this. We don't need the meter because we're just going to watch the effect on the compass. I'm going to put this coil here. Oh, we put the coil over here. Okay, the compass is still pointing to
Should I get closer?
north. Yes, you make it closer. And then we got a battery person here. What he's going to do, he's going to inject a current through the coil and watch what happens to the compass. You see there's a little bit of an influence on the compass right there.
Here it goes.
Flip around the other way, let's see. Let's see if we got it good.
Could you put it on top and see what happens?
Oh, there you go.
Oh.
Yeah, look at that. And the orientation of the coil does have
There it is.
an interesting impact too as well. Notice the coil face there. Take that loose.
Okay, now we can see it.
So that's normal. One direction.
Now you did that. If you flip it around, it points the compass the other way. See that? So the electric current producing the field through the coil is actually acting like a magnet. So it's the basic concept of how we produce electricity and use it. When we produce it, we move the magnet through the coil. Okay. When we use the electricity, it's like a fan or a motor. You take the coil and you move the magnet, which treat the compass as like being a magnet. So that's the relationship of electricity and magnetism. Any other things you want to add to this?
No, that's good.
You got it? Okay. Thank you.
Thank you.